And so what we do with that, these are called outliers in computer vision, which doesn't make much sense to statisticians because they want to take them out of the data set completely. So another term that gets thrown around is called blunders, and I don't like that one much either. But that's what I did my research on last summer at Los Alamos, was blunder detection in these 2D transformations. And I'll show that in a little bit. So there are plenty of ways to deal with getting rid of these outliers. And the one that I've used and the one that's very common is called RANSAC, or Random Sample Consensus. And so essentially what you're doing is starting with that model, right, that takes 1 or 2 or 4 points to calculate the transformation. And you're selecting however many points you need to make it, so 4 or less. And then you fit the model just on those 4 points. You see how close, you calculate your residuals for all the other points in your data set, see how many of them are below some threshold. And you're trying to get the largest set that fit under that threshold. And so if you get one of those outliers in your model, you're going to find less points that fit under the threshold because it's far away from the other ones. And that's essentially how it works. And so it keeps going until you get the biggest set of inliers that you can find, so points that fit under that threshold. So this isn't necessarily specific to computer vision. It can be used in regression, which I'm going to draw. I promised I wasn't going to draw. So you've got some points that definitely fit your model and some points that definitely don't. But if you were to fit least squares, it would probably look like that, right? But you want it to look like that. And so RANSAC can pick out these pieces and throw them out if you have some idea of what your model can look like. So that's kind of what it's doing in a 2D sense. And those pictures not showing up. Perfect. I'll show them at the end then. Oh, showed up for a second. Anyway, so now we have these transformations that we can measure between images. And like I said, sometimes you want to combine more than one image at a time. And so essentially a panorama, even when you do it on your phone, is just combining these images using the transformations between them. So it's measuring translation, rotation. Usually you're not scaling while you take a panorama, but it could happen. And combining them using those estimated SIFT features. So it's matching up the points and then using that to overlap them. And so it projects them all onto the same common plane so that they're not angled anymore like they were when you took them. So that only works up to 180 degrees. And after that, they're projecting them onto a cylinder because you're going all the way around. OK, so that's images at one point in time. And now we want to look at over time. So a video is really just a sequence of images, usually over quick amounts of time, collected at one time. And now we've got 3 variables that we're measuring over, x, y, and t. So places it's used in computer vision, background subtraction. So if you have somebody moving around on like a basketball court, the court's not moving. So if you keep the same frame, you can remove them from the court and just look at their motion. Right? Any singular object that's moving, you can pick it out of the background. And then once you have how far a point in image space is to the real world, you can say, oh, they moved 10 feet over these images, that kind of thing. And then you can estimate velocity and acceleration and all kinds of things, which is what they do with NBA data. Shot boundary detection, so if you're looking at a video and it changes from one scene to a different scene, you can measure that change because there's obviously a big change in what the image looks like. And so you can figure out where a scene would end and another scene would begin using that, which is useful for people who create videos and highlight reels and things like that. Motion segmentation, so if you have more than one object moving at once, you can pick apart each person's motion. So if they're all walking in different directions, you can isolate them essentially. Recognizing events, so if you have common motion happening, what does that mean, essentially? And then improving video quality. So once you know the relationship between those images, you can cut down on noise that's occurring from the video moving around. So you can combine them kind of like a panorama over time. Okay, so I'm not going to go too much into this, but essentially they use feature-based methods, which are using those SIF features that we just talked about, tracking them over time, and then these direct dense methods. And so all you really need to know is that the feature ones give you more robust tracking, and the dense ones are sensitive to appearance. So things like brightness in the image. If you're outside, that's going to make it harder to understand where something is or where it went. Yeah. And so one of the dense ones is called Optical Flow. And essentially you're looking at where it thinks something went. And so in this image, this is on a spinning wheel. But since this whole wheel, the top part is the same color, it can't tell that it moved. Right? So you run into issues like that with color and or intensity in this case, as well as shape. So we can't necessarily tell which way this is oriented because it's a cube. And so one of the methods for implementing this flow idea is called Lucaskanade. And basically what you're trying to do is assume that all of your pixels in a certain neighborhood are moving in the same way. And from there you can kind of estimate the corners between them and do everything else. And so the issue with this is a lot of times you're moving more than one pixel at a time. Right? You're moving fast, or you're moving at a large scale. I think this goes to a YouTube video. Yeah, okay. So he's trying to track this part of the cup. And you can see as he moves it and rotates it, it's still following that part. So that's the way the Lucaskanade works. And then he tilts it, so that's a different transformation, and it can still follow it. And you can see that green path that it's keeping track of where it's been. And so right now it's doing detection. So essentially it's finding the object independently in each frame. And so in a couple minutes I'll talk about tracking, where you can use where you were in previous frames to help update where you think you are now. And how do I get over here? There we go. Okay, so that's Lucaskanade, and that's a super popular method. And so like I said, the issue is that usually you're moving more than one pixel at a time. But this is only really good for measuring small amounts of motion. So the solution is to scale your images down so that your motion looks like it's only happening over one pixel at a time. So they use these things called Gaussian pyramids. And so you scale the images down by half size at a time. And then you go to the smallest ones and you run your Lucaskanade. Then you bring it back up a scale. You fit it, you correct errors. You do the same thing over and over again. So it's an iterative process. And then you have an estimated version of what your motion looks like on the normal scale. Okay, so yeah, like I said a second ago, detection is when you're looking at motion independently in each frame, and tracking uses the dynamics that you already know from previous images to figure out where it's been. So this kind of lends itself to a Bayesian perspective, because you're updating where you think you are based on where you've been, so as you get new data. And so one of the issues, yeah, like I said, it's hard to compute optical flow sometimes because large objects move rapidly, other objects get occluded, so they can disappear, reappear. And then as you get errors in methods like Lucaskanade, they compile over time. And so as something starts moving faster and then slower, or somebody runs in front of it, it's hard for it to fix all those errors because it's tracking, or it's detecting each thing independently. So it doesn't know what has happened before. And so we start using, we kind of frame this as an inference problem, which makes sense for statisticians. So we've got some state of things that are going on. Usually this is just our x and y that we're trying to figure out where an object is, or where the center of an object is. And then we measure it at each frame, so we can observe it in the next image. We can use that as our measurement. And then basically we're trying to figure out where an image is at time t based on where it's been and based on the dynamics that we know about how it moves. And so there are different dynamics models that you can use to understand how things move. And so, yeah, we go back and forth between this prediction and then we observe new data, and then we correct the prediction. And then we go through it again, so it's a cycle. And so tracking is essentially this propagation through the posterior, given the measurements and some prior understanding of how the state moves. And so we use probability because there's noise, and sometimes in video there are missing frames or occlusions. So something disappears. We don't have any data for where it is at that point in time. So we just have some most likely place that it is. And so one of the common methods is called a Kalman filter. And essentially it's fitting what's called a linear dynamic model or dynamic linear model. And again, it's going through this cycle of measuring, correcting, going to the next time step, predicting, measuring, correcting. And this is used in areas outside of computer vision as well. And the limitation of this is that it thinks your predicted and corrected states follow a normal distribution, which is good for certain types of motion and not good for other types. So then people turn to Bayes filters. And essentially you have a prior probability of where this thing started. You have some dynamics model of how it moves, and you have this likelihood. So if the object was really at some place, what's the likelihood that I measured it correctly? And then you continue to get this stream of data over time. And again, we're trying to estimate this state x at time t. And so the state is really whatever you are trying to understand about the image. So it could just be the position, it could be the shape of it if you want to track multiple points around it. So in basketball, if you're trying to track how far apart the players are, you use something called a convex hull. And so you can measure that area, and that'll change over time. So that could be your state, depending on how you frame the question. Yeah. And so one interesting application of these Bayesian filters are particle filters. And essentially, you start by sampling a bunch over your state, right? And so if you have an uninformative prior, you're going to probably sample uniformly over the course of the image. And then as the dynamics go on, you start resampling at each time frame, but you weight it based on what you've learned about the image. So you get these patches of where you think it's likely to be. And so this is really useful because you can have multiple hypotheses about where it is, because there could be multiple places where it's likely to be, especially if you have like a symmetric room or something that you're moving around. And then, yeah, higher weight is a place where it's more likely to be. So this is how that works. So it's resampling all these yellow particles, and then in the purple range, that's where it's most likely to be. And you can see people occluding it, and it'll kind of jump and get more uncertain. But since it knows what it's tracking, I'm not sure what they used to their state here. I think they probably used the color of his code as well to help that. So yeah, then it gets really confusing. It'll jump to other objects that are moving, and they staged this so that people would walk by. Hopefully. Really got really lucky. So that is particle filters. And those are used a lot for robots. So if you have a robot and it kind of understands the map that it can move around in, it can send out, its likelihood model could be a sensor, like how far am I from a wall? So then you get an orientation to these walls, and you get a distance, and it learns kind of where it is in that room over time. Okay, so I have like 10 more slides. So basically everything we did up until now, the computer doesn't know what is in the images. It just knows that they're data. And so what we want to do now is called recognition. So we're trying to learn that the image is made up of people or chairs or dogs or cats, things like that. And so this is where machine learning can really be helpful if we have training data with labels. And so there are different approaches and different things that you might try to learn. So verification, am I looking at this specific object? Detection, are there people or faces in this image? Identification, am I at a specific location? If you have enough images of a scene, you can figure out where you are. And then object categorization is a really popular one. And it's one of the things that they're still having trouble solving in computer vision. Mainly because our definition of a tree is very vast. So it could be lots of different types of trees, different heights, different colors at different times of year, things like that. And then scene context categorization. So this all looks like I'm outside. And that's also an open problem that's very hard because you basically have to do a bunch of object categorization and then figure out what that means. So they break it down into kind of generic levels. So I'm looking at a car. More specific, I'm looking at my car. And the computer doesn't necessarily know what my car looks like. So you have to have very specific training data that would match up with whatever you're trying to learn about it. And so we're not trying to take too much data, so we're trying to do it with as little data as possible, essentially. Yeah, and the problem is that they don't have unique labels. So depending on who created the algorithm, they may have labeled them differently. They may have different spellings if they're from different countries, things like that are all issues they run into. And so issues with this object categorization, as you saw in that video, there are crowds often, things get cluttered, and there's overlapping objects. So if you have two cars, you can only see part of the second car. Do you know that they're different cars? How do you separate them? Things like that. Robustness to things like illumination and pose. So if I'm, if I have my hands up, am I still a human? What is that? What kind of thing does that mean? So if you don't have that in your training data set, it doesn't know that that's the same kind of object. And so you have to have these large and diverse training data sets. And then viewpoint, yeah. And so this gets very complex because in a lot of images, we're having higher and higher resolution cameras, so there's more pixels to look through, which means more time in these matrix calculations, essentially. And then there's also, I think the number I kept seeing was about 30,000 categories of things. So that gets wider and wider as time goes on. And so it takes humans about 6 years to learn what those categories of things are, and we're trying to teach a computer instantly. And then the importance of context. So does something mean the same thing in a different situation? That's something that humans even have trouble with. So teaching computers is hard. And there's not necessarily like a set framework for how to do that yet, because it's still a very new field. So then we turn to supervised classification. And basically we have labeled examples, and we're trying to predict the labels for new examples. And so they break this down in two main ways. We have these generative models, where you're modeling each type of thing, and discriminative models, where you're looking at the boundaries between types of things. So the generative models came first. That was originally what they thought of, but the advantage is that you can add new types of things, and those models are independent from the previous ones, so you can keep adding them and adding them. The problem is that we don't necessarily care, if it's this thing or this thing. We want to know what part of it makes it this thing or this thing. So we really want to discriminate. So those are where a lot of the algorithms are focused now. We want to know what part of the image makes it discriminable. So for these generative models, again, you have these classes, and you're trying to pick some maximum of your likelihood, essentially. Which brings it into statistics world. And usually you can use parametric models with Gaussians and things like that. The one that's super popular in computer vision is principal components. Really what you're doing with these images is breaking them down into parts that are in the components of variation. And so from this, from a set of faces, we can say different parts of the face make it easy to tell whether it's a face or not a face. And so usually in images, they're not zoomed in that much, so most of the image is not a face. So we can quickly tell from like the first principal component that it's not a face and move on. And then discriminative models are really just classification problems. So you build a model, you train a classifier, you generate new samples, and you figure out which class it's most likely to be in. So these are some of the common ones that are using computer vision. They're very big on boosting and SVMs, and they're starting to get more into random forests now. And then one cool face detection method that came out of boosting is this Viola Jones method. And essentially what they did was take a giant training set of faces and non-faces so you can tell the difference between them. And non-faces is a much bigger class, right? Because anything that's not a face falls into non-face. So they had to be careful about that. And what they do is they get these rectangles that they call integral images. So basically, you're looking at the difference between the dark part of the rectangle and the light part, and that can tell you whether it's a face or not. So if you look at this first one, that's right over where your eyes would be. So they can tell by the difference between your eyes and your nose area if it's not a face right away. So they can rule those out and have less data in the next iteration. And then it goes down to like the side of your neck and things like that. So that's a fairly recent and pretty cool thing. And then I think I'm pretty much done. So the last thing I'll talk about, basically you can think of images in a similar way to text analysis. So you can come up with these visual words that make up an image. And when you get tons of new data, you can just see which words fit the image best. And so you can understand what's in it based on which words it's made up of. And so that's a fairly new kind of classification method, but the problem with this is you need tons of training data as well to get lots of words. And your training data has to be of the same things, because if a car is facing a different way, you'll get different words out of it. You can't necessarily find a different car later. Things like that. So that is all I have. There's plenty of stuff in computer vision that I didn't talk about, but I hope you picked up a little bit about how computers view images. From here, you can look at color images, more into video analysis, and scene understanding, which are hard and open problems. And then OpenCV is an open source library that you can use in Python and MATLAB and Java and tons of other things to implement algorithms like these. So that's all I got. Any questions?
You mentioned with robots they can do include other sensors and things.
Mm-hmm. Yeah, so they could have like on self-driving cars, they use computer vision, and they have more than one kind of sensor, and also more than one camera. So they use, I think, something called LiDAR as one way to tell light and distance and things like that. And then they also use radar to go in multiple directions, so they can see cars around them. Yeah, so basically, when you go to these things like Bayesian filters, your sensor model isn't necessarily just one thing. It's all of the things that you're measuring in each image. And so it can become a high-dimensional thing, depending on how many parameters you're trying to estimate. But yeah, it's not limited to just one sensor at a time. Anything else?
You mentioned pictures getting more and more megapixels. Do they downscale somewhere along the algorithm path just to speed up the process, or how does that?
That's a good question. So I think part of it depends on the image format that you're using. So things like JPEG essentially have compression algorithms, so that if you want to shrink your JPEG, you can retain almost all the same information. So it does depend on that. I don't know how these algorithms deal with it. I think usually people are just trying to put in the bigger images and wait longer.
What was the slide with Gaussian pyramids?
Mm-hmm.
Is that downscale, or is that something else?
So usually in that case, they're starting with these bigger images and downscaling, yeah, in terms of finding motion, because they want their motion to be about a pixel wide so that they can estimate it. Otherwise, there's big jumps and they can't tell where it went in between those pixels. So you could do it that way, but I think the bigger the images get, the more you lose when you upscale on the way back. Because it's kind of like doing a derivative and an integral. So you can take derivatives and retain the same information, but when you take an integral, you have that constant of integration that you're off by each time you integrate. So you're losing more and more information the more you have to downscale.